Hi, welcome back to the Mentored Engineer. Today we're going to be looking at sizing our pin. We want to make sure that we have all of our load cases in here. So we've already calculated our reactions A and B at any angle, but what we haven't done is look at how another load case would affect it. This load case is side loading. Alright, now when I pick up a log here and I'm going to pick it up and I want to be able to turn it. And the way that this log splitter, it's not automated or anything, it's powered by, me. And I have to grab here and push that point away. And basically what happens is I can develop a lot of force. The heavier this is, the more friction there is in this joint here that doesn't want to rotate. Okay, so what I need to do is come up with a force that's realistic. I thought about using 50 pounds, but I think that's just a little bit too small. Maybe 75, but for this example, we're just going to use 100 because it's a nice round number. 100 pounds going in and out of the page. All right, so it's going to cause a moment up here at this pin, and we want to be able to solve for that. So our moment, and I'm going to subscript it with side load, SL, is going to be equal to 100 pounds times our length times the cosine of the angle, which is theta here. And that's going to be our moment. So now let's take a view of this joint up here, how this attaches. Alright, so when we look from the top view, we're going to see our tube, and then it'll kind of be our anchor point here. We'll have two clevises. And for this example, I would recommend that they're equal width. These ones are very thin, they're quarter or maybe 3/8 of an inch thick. So they're not going to be, we could assume a uniformly distributed load on them. If they get really thick, we know, if it was 2 inches thick, the edge is going to get the load. So we'd have to make some assumptions of how much of it gets the load here. But these are very thin. The load will distribute fairly well. Alright, then we have our member here that moves. This beam right here, that's this. So what we're going to do is we're going to start labeling things. We're going to get our center to center distance, and I'm just going to call it CC. We're going to have width 1, width 2, and width 3. I would also recommend that width 1 and width 3 be the same thickness for this application. We push it one way and we're going to get stress. We push it the other way, we're going to get the stress on the opposite ear. And that's the difference of stress is going to be caused by the A and B loads. So don't see a reason to have different thickness ears here. The other thing we need to keep account of is our gaps. So we're going to have gap 1 and gap 2. So pins, they don't like bending stress, which is why bending is most times the limiting factor. With pins, you have gaps that can go from side to side. So as we look at this, we're going to calculate our moment as we go this way. And we want to maximize gap 1 and minimize gap 2, which essentially just means it got pushed over to one side. Alright, so let's get started. The first thing we're going to want to find out is what is our reaction force on those ears. Alright, so our force of side load is going to be simply the moment of the side load divided by the center to center distance. Pretty simple. So now what we're going to want to do is we're going to want to make a shear moment diagram. So let's look at the shear part. Starting at 0 and ending at CC, we're going to have the force of the side load, right, and that's going to go for some distance. And then we're going to have a reaction here in this W2, and that's going to go to 0 in the middle, and then it's going to come over here, and eventually we'll even out. So let's label some spots here. Alright, so this would be the distance from the center of this web, of this clevis, to the start there. So that'd be half of the thickness of that member, plus gap 1. So from these two triangles right here, we need to know what that is, and that's simply the width of the beam that is supporting the load. So now what we're going to need to do is integrate the area under the curve up to this point right here. All right, and that's not hard to do. It's pretty easy. It's just, all right, it's integrating is the area under the curve. So all we're going to do is we're going to say our moment is equal to the force of the side load times this distance. That's the first component. All right, and then we're going to add in the area under this triangle right here, which areas of a triangle is half the area of a square, so we'll just divide it by 2. So there's the force divided by 2. And then we have the width 2 also divided by 2, since we're only going to the midpoint of it. And we add those two together and get our side load.